Okay, so in this video, we're going to be talking about energy 1C, which is related to solving problems with conservation of mechanical energy. Now, this is going to be the last section in the energy unit, and probably the section involving the most math. So definitely make sure you take good notes, pay close attention, ask questions if you need things clarified, and yeah. So, just to recap, we talked about this in all of the videos so far, but basically in physics we have this really important theorem called the conservation of energy. And the idea behind the conservation of energy is that energy is something that cannot be created or destroyed, but there are different forms of it, and energy can transfer from one form to another form. Okay, and so far we've learned about different types of energy, specifically kinetic energy and gravitational potential energy. Okay, and so with that in mind, we can do basic calculations with energy conservation. The most common types of energy that you've seen in this unit, like I said, are kinetic and potential energy. And basically, if you add an object's kinetic energy to its potential energy, you get what's called mechanical energy. And so we have this thing, we will call it EMEC. EMEC stands for mechanical energy, and it's basically going to be Eg plus Ek, the gravitational potential energy of an object plus the kinetic energy of an object. Okay, and so it's definitely possible for an object to have more than one energy at a time. Now, we're going to do some basic calculations calculating mechanical energy, but the reason we're talking about mechanical energy is because we're going to be doing problems where mechanical energy is conserved, and conservation laws are very important in physics, and so it's important that you are able to do calculations with them. So before we get to conservation calculations, let's do some basic mechanical energy conservation, or some basic mechanical energy calculations. So, example 1. It says a 45,000 kilogram airplane flies at a speed of 240 meters per second. As I'm going through, of course, I'm identifying all of my given information. Here we have the mass in kilograms. We have V, 240 meters per second, while traveling at an altitude of 2,000 meters above the ground. Now, if you don't know what that word altitude means, that's basically the height above the ground, which it says in the problem. And so this is going to be h. Now the first thing says calculate the kinetic energy of the airplane. Well, kinetic energy is energy of motion, and that's just 1/2 mv squared. And so this is a very simple calculation. That's going to be 1/2 times 45,000 times v, which is 240 squared. Okay, so I'm just going to type all this into my calculator. Okay, and it is going to be a very big number, but that's to be expected because it's an airplane. Okay, so the number I get is 1296, and then it looks like I have 1, 2, 3, 4, 5, 6 zeros. Okay, so this is quite a large number. Okay, and so if I put my decimals in here, I can see this is basically, 1.3 billion joules of energy. Okay, which again, that might seem like a lot, but we're talking about an airplane that's really big, moving really fast. Now the gravitational potential energy, which is Eg, that's just mgh. Okay, so that's going to be the mass times g, which is the acceleration due to gravity. Remember, we use a value of 10 on Earth for that, times the height, which in this case is at 2,000 meters. Okay, so far this should be very easy. Okay, we're just simply plugging into our equations. So I get 9, okay, and then I have a certain number of decimals. Let me see how many decimals that is. It looks like I have 9, 0, 0, 0. Actually, messed up on that comma. Looks like I have 8 zeros. Okay, so let me just write out the zeros first. 9, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that is actually 900 million joules. So, what is mechanical energy? Remember that mechanical energy by definition is the kinetic energy plus the potential energy. So all I'm going to do is I'm going to add those two numbers from the last question together. Okay, so give me just a sec to do that. Okay, if I did that correctly, I should get 1, 3, 8, 6, 0, 0, 0, 0, 0, 0, joules. Okay, so over, what is that? I guess 1 billion joules. Okay, all I did was add those two numbers together. Okay, so again, mechanical energy, just the kinetic energy plus the potential energy. Pause there if you need to look at that. Let's do another quick example. Okay, example 2. A 4,500 kilogram roller coaster. Again, immediately I jump into reading the problem and I'm identifying my given information. Pay close attention to units. Okay, so mass is measured in kilograms. A roller coaster cart rolls down a hill which has a height, here's my height, of 25 meters. If the cart is moving at 12 meters per second, that's meters per second, so that's going to be V. At the top of the hill, calculate the kinetic energy, the potential energy, and the mechanical energy. So this is very similar to example 1. Okay, so this is nothing other than plugging numbers into an equation. 1/2 times 4,500, sorry about my bad handwriting, times 12 squared. And then for EG, it's just going to be mgh, so m times g times h. Okay, and I'm just going to type both of those into my calculator really quickly. 12 squared times 1/2 times 4,500. Okay, let me adjust my calculator to give me the correct answer. Okay, so the kinetic energy is 324,000 joules. The gravitational potential energy is 4,500 times 10 times 25. Okay, that looks like a bigger number. Okay, so 1.125 million joules. And then the mechanical energy is just, again, the kinetic energy plus the potential energy. So all I'm doing is adding those two numbers together. Okay, so far, nothing challenging. Hopefully nothing challenging. Okay, because we're about to get into the more challenging stuff here in just a sec. Okay, so that is the answer for example 2. Again, pause there if you need to take a look at that. Okay, so now that we have this idea of mechanical energy, let's see what we can do with it. Okay, so we talked about conservation of energy before, and energy is always conserved in the universe. Okay, but there's something called conservation of mechanical energy. Now, if a special condition is met, then the mechanical energy of an object can also not change. It's also a fixed value that cannot increase or decrease. Okay, so here's the condition. If there is no friction or no air resistance, we say the mechanical energy of that object is conserved. Okay, that means it has some set amount of mechanical energy that does not change. Now, the way we solve problems with conservation laws in physics is basically we say that you have like an initial value and a final value, and those two are equal to each other. Because, if your initial and your final are the same, that basically means that you didn't change at all. Okay, so this is how we write the conservation of mechanical energy. We say E mech I, that means the starting mechanical energy, is equal to E mech F, that means the final mechanical energy. Okay, and so we're going to see what problems look like for this in just a second. But remember, both E mech I and E mech F are kinetic plus potential energy. So that means E mech I is the initial kinetic energy plus the initial potential energy, and E mech F on the right side would be the final kinetic energy plus the final potential energy. Okay, so we're going to use this equation. This is our conservation of mechanical energy equation, but we're also going to use the definition of mechanical energy, which we've been using in the last two examples. It's kinetic energy plus potential energy. So let's see what problems look like with conservation of mechanical energy. Okay, and again, this is the last thing in this unit, but it's also probably the most difficult calculation-wise, so pay close attention. So let's start with example 1. It says a ball is dropped from rest from an initial height of 12 meters off the ground. Now, I'm going to, it looks like I forgot to give you the mass, so let's say a 1 kilogram ball is dropped from rest. Okay, so we have the mass of the ball, so I'm going to label that as M, and it says it's dropped from rest. Now, we talked in past units about how if you're at rest, that means you're not moving, and that means your speed is 0. Okay, so that means V equals 0. All right, but remember that because we're dropping the ball, we have an initial value and we have a final value. And so I'm going to say that V initial is equal to 0 because it's dropped from rest. It says we have an initial height of 12 meters. Okay, I'm going to label that as H for height, and then I for initial height, 12 meters off the ground. Calculate the speed of the ball. Okay, so I'm looking for V. I already have VI, so this must be VF. That's my unknown. When it is 2 meters off of the ground. Okay, so basically at the beginning of the problem, it's 12 meters off the ground. At the end of the problem, it's 2 meters off the ground. So this is still a height because it's still in meters, but it's going to be my final height. Okay, now here's how you solve problems with mechanical energy conservation. This is my mechanical energy conservation equation. E mech I equals E mech F. But what I'm going to do, because mechanical energy, remember how you calculate mechanical energy, that's just kinetic plus potential energy. Okay, because E mech is kinetic plus potential, I'm actually going to expand out both sides of this equation. In other words, instead of E mech I, I'm going to write that as EKI plus EGI. And instead of E mech F, I'm going to write EKF plus EGF. Okay, in other words, I'm just plugging in to this equation, the original equation for mechanical energy. Okay, now I'm going to expand one more time, and I know this seems like a lot, but that's how you solve these problems. I'm going to expand one more time because I actually have an equation for EK. It's 1/2 mv squared. Plus, I have an equation for EG. That's mgh. So I'm actually going to expand this equation one more time. Watch this. Okay, for EKI, I'm going to write 1/2 mvi squared plus, for EGI, I'm going to write mghi, and I'm going to do the same thing over here. This is going to be 1/2 mv final squared plus mgh final. Okay, now this is my conservation mechanical energy equation, but the most useful form of it, most likely, is going to be this bottom form down here, because this is the equation I can directly plug numbers into. Now again, it seems like a lot, but once I get to plug numbers in, you'll see it's really not that bad. So what I'm going to do now is I'm going to go up here and I'm going to start plugging in my given information. So watch what I do. 1/2 times the mass, which is 1. VI, it was dropped from rest, so V initial was 0. So I'm going to put 0 squared plus, okay, then the next thing is going to be mghi. Okay, so that's going to be 1 times 10, that's G. HI was 12, is equal to, I'm going to put the equal sign down here because I'm going to run out of space, is equal to 1/2 mv final squared. Okay, we don't know v final, so I leave that in the equation. That's what I'm solving for. Plus mgh final, which was 2. Okay, and it looks way worse than it is because I can actually simplify a lot of this. First of all, 1/2 times 1 times 0 squared, that whole thing is going to be 0. Because when I multiply by 0, this whole thing is going to be gone. Okay, so I have 0 plus 1 times 10 times 12, that's 120, equals, okay, 1/2 times 1, that's 0.5, v final squared, I still have to leave that in there because it's unknown, plus 1 times 10 times 2, which is 20. And so from here, all I need to do is rearrange this and get VF by itself. So I need to do a little bit of algebra. I'm actually going to erase this 0 over here because I don't really care about that 0. Okay, and so I need to subtract 20 on both sides, minus 20, minus 20. Okay, that's going to go away. I end up with 100. I guess I will write up here 100 equals 0.5 VF squared. Now there's two things being done to VF. It's being multiplied and it's being squared. So I'm going to deal with that multiplication first by dividing. both sides by 0.5, like that. And then I'm going to simplify. Now I need to erase because I'm starting to run out of space over here. Okay, so I'm just going to erase a little bit over here now. Actually, I will erase this part up here. Okay, so I have 100 divided by 0.5, that's 200, equals VF squared. And then my last step is to square root both sides to undo that square. Okay, now the square root of 200, I type that into my calculator, and I get 14.1. Okay, so 14.1 meters per second, that is V final. And so that is how fast the ball is moving 2 meters off of the ground. Okay, so it was dropped with no speed, but as it falls faster and faster. Okay, so that's the speed 2 meters off of the ground. So that is a full-on conservation mechanical energy problem that we just did. Okay, so we're going to do one or two more examples. But if you can do this type of problem right here, then you can probably do any of these mechanical energy conservation problems, because this is about as difficult as you might expect. Okay, so definitely pause it there. See if you can figure that problem out, and then we're going to go into example 2. Okay, so I'm going to erase this. Example 2. Now, example 2 says, in the diagram on the right, the 400 kilogram cart, okay, so there's the mass, starts from rest on top of the 90-meter hill. Okay, so in other words, right here, it is at rest. That means I can label V initial 0. Okay, now I'm also given in the picture that the height at this point is 90 meters. So I can also say that H initial, the initial height, is 90 meters because that's where it starts from rest. That's the height at that location. So I have VI and I have HI. Now the first question says calculate the mechanical energy of the cart at the top of the 90-meter hill. Well, mechanical energy is just kinetic plus potential. Okay, so I need to find the kinetic energy and the potential energy and add them together. Now the kinetic energy of the cart is 0 joules. Now normally I would plug into the equation to find kinetic energy, but I don't have to do that because it tells me that the cart starts from rest. If it's not moving, it has no kinetic energy, because remember, kinetic energy is energy of motion. So EK is 0, and then EG, which is MGH, okay, that's going to be 400 times 10 times the height at that location, which is 90. Okay, so again, I go to my calculator. I plug in 400 times 10 times 90. I get 360,000 joules, and that is my mechanical energy at that location. Okay, at the top of the first hill. Now it's very, very, very important that you understand the concept of mechanical energy conservation. If this is the mechanical energy at the top of the hill and mechanical energy is conserved, that means the mechanical energy everywhere else has to be the same number. Okay, it has to be this 360,000 joules, okay, that I started with, because mechanical energy is conserved. Remember in the simulation that we saw, the energy can change form from one form to another, but the total amount remained the same. Okay, this is basically what we're dealing with. So as the cart goes down the hill, it's going to lose gravitational potential energy, but it's going to make up that difference in the form of kinetic energy. So the total amount of mechanical energy is the same. I know right away that the mechanical energy at A is 360,000 joules. The mechanical energy at B is 360,000 joules. Okay, because mechanical energy is conserved. That's the point. Okay, the total amount doesn't change. It's the same. Okay, it just changes forms. So the last question says calculate the speed of the cart at point A. So now I use my mechanical energy conservation. Emec I equals Emec F. I expand that thing out just like I did before. Okay, and so I'm just going to write the whole thing. That's 1/2 MVI squared plus MGHI equals 1/2 MV final squared plus MGH final. And then I plug in. Okay, but I actually don't have to plug in as much as you might think, because this thing on the left, I already did that calculation. I did that calculation right up here. Okay, so this thing on the left, I already know what goes on the left. That's 360,000 joules. Actually, I don't need to put the unit because I'm plugging into the equation. Okay, just 360,000. So all I need to do is plug in on the right side. On the right side, I have 1/2. The mass is 400. V final is unknown because I want the speed of the cart at point A, and then I need to do mgh for point A. Okay, now that would be 400 times 10 times the height, but look at point A. What is the height at point A? Okay, hopefully you can see in the picture the height at point A is going to be 0 because point A is on the ground. So normally I would plug it in here, but I'm kind of running out of space, and to be honest, it's going to be 0 anyway. Okay, and so I'm just going to put 0 there. Because the height is 0, that makes the whole thing 0. So I have 360,000. I think that's too many zeros. Okay, let's try that again. I have 360,000 on the left equals half of 400 is 200 squared. Okay, and now I'm going to erase some stuff at the top just so I have space to write. Okay, and so these problems, as you can see, they might take you some practice, okay, for sure. That's normal. That's to be expected. So now I'm going to finish off the problem. I have 360,000 equals 200 times VF squared. I need to divide both sides by 200. So I'm going to do 360 squared. 360,000 divided by 200 equals V final squared. And then I'm going to take the square root after that. Okay, so first I'm going to divide 360,000 divided by 200 equals 1800, and that is equal to V final squared. And then I'm going to take the square root of that number. Okay, so I plug that into my calculator, and I get VF equals 42.4 meters per second, and that is the answer to my question. Okay, so that is example 2, another conservation of mechanical energy question. Okay, so mechanical energy conservation questions, there is a lot of work involved, no pun intended. You do have to identify a lot of variables, but this is how you set them up. Okay, so we're going to take a look at one more quick example that has a little less calculations, and then you should definitely work on your practice worksheet. Please, please, please let me know if you have any questions. Okay, pause it there if you need to look at that. Okay, I'm going to erase this. Okay, example 3. Okay, so we have a picture here, and it says a 1 kilogram ball can either roll down a frictionless hill as shown, or it can be dropped from the top of the hill directly towards the ground. And we're asked to solve for some blanks. Now, again, the key concept here is mechanical energy is conserved. That means the final and the initial mechanical energy are the same. Don't forget that mechanical energy, when we talk about mechanical energy, we mean kinetic plus potential. In other words, the kinetic plus potential is always a fixed number. Now, as long as you understand this concept, okay, this question is actually pretty easy. So look at the top of the hill. We start with 100 joules of potential energy plus 0 joules of kinetic energy. So that means the mechanical energy at the top is 100 plus 0, which is 100 joules. Because mechanical energy is conserved, guess what? That number never changes. So that means when the ball goes down to here, look at what it says. It has 50 joules of potential energy, but we know overall it has to have 100 joules of mechanical energy. So if it has 50 joules of potential energy, that means at A, it must have 50 joules of kinetic energy, because 50 plus 50 makes 100. Now, at blank B, blank A and blank B are at the exact same height, or I don't know why I said blank B, sorry. At this position right here, they have the same height, and so I can tell you right now that it's basically going to be the exact same. It's going to be that 50-50 split. Okay, now I'm going to skip blank B just because it's a speed calculation, and I want to not make this video super long. Okay, but you would solve for V basically by just using the kinetic energy equation, 1/2 mv squared, and plugging in and solving for V, because you know that the kinetic energy is 50 joules. Okay, so for blank C and D, I told you it would be the same as in this position. At the bottom, when there's no height, if there's no height, there's no potential energy. That means blank I would be 0 joules. But guess what? You have to have the same amount of mechanical energy because mechanical energy is conserved. So if this is now 0, that means blank J has to be 100 joules, and so on and so forth. And so hopefully that gives you an idea of how to approach these problems. See if you can do the rest on your own, and if you want to check your answers, you're welcome to email me. I'll be happy to check your answers for you for example 3. So, as always, please let me know if you have any questions. I know that was a long video, I apologize for that, but this is the last video in the energy unit. Okay, if you need to rewatch anything, definitely go on YouTube and rewatch parts of this video. Okay, so as always, let me know if you have any questions, and I will see you guys in the next video.